Welcome to this video lecture in thermodynamics. Today's lecture is going to talk about the engineering approach to problem solving. We're not going to cover any real technical material in this lecture. It'll be more on just your approach to working assignments and just engineering in general. So let's go ahead and get started. Take a look at your screen. The picture here is just of an engineering team trying to solve some sort of problem, just trying to find some sort of representative picture here. Let's not focus too much on the image. Let's just go ahead and get straight into the material. One of the big things that we'll be talking about in this course that you've had a little bit of exposure to perhaps already is the use of what are called energy flow diagrams. Now I know you probably haven't used an energy flow diagram in any other course, but you may have used free body diagrams in a course like statics or physics or dynamics or something like that. And engineering flow diagrams are very similar to that. And I put some bullet points here on the screen just to kind of explain this. So we'll be using energy flow diagrams, or EFDs, when we do analyses involving conservation of mass, the first law of thermodynamics, and the second law of thermodynamics. Those are the three main fundamental laws that we'll be using in this course. And we'll have to use these energy flow diagrams for all of those. As I mentioned, they're similar to free body diagrams used in statics and dynamics in the sense that what you're doing is you're identifying what it is you're analyzing and then drawing all the relevant interactions of that object with the surroundings. So you'll see what I'm talking about in a moment. The third bullet point is identify your system or control volume using a dashed line, and then the fourth bullet point is to identify relevant transfers of mass and energy. And the energy transfers typically, well, they take place either as via heat transfer or work, and we'll learn more about that in a later lecture. And we'll identify those transfers of energy across the boundary. Okay, so this is the kind of thing we're talking about here. So first of all, I have some online examples that you can take a look at where I do generate some of these energy flow diagrams so you can see some examples of them. But let me just go through a simple one right here. Let's say we're interested in, let's draw a light bulb, okay, an old-fashioned kind of light bulb, like an incandescent bulb. And I'm not very good at drawing light bulbs, but imagine this is our light bulb, right? And there's a filament that's in here. And I want to analyze that light bulb. I want to do some kind of thermodynamic analysis to it. So the first thing I'm going to do is I'm going to identify the light bulb as the system that I'm studying. And I do that with a dashed line. Okay, so I'm going to draw a dashed line around the light bulb to indicate that that light bulb is my system that I'm examining. Okay. You'll learn, well, I guess we talked about it in a previous lecture, the difference between a system and a control volume, but they're essentially similar things. A system is a particular quantity of matter chosen for study, in this case our light bulb. A control volume is a particular region or volume that's chosen for study. So one's focused on matter, the other one's focused on a volume. In this case, they're basically the same. I'm interested in the light bulb and the volume surrounding the light bulb. But the important thing is I'm identifying it with this dashed line so that everybody knows what it is I'm talking about. And then what I'm going to do is identify the relevant transfers of mass and energy across the boundary. Now there is no mass transfer across this boundary, right? You don't have any mass coming into or out of the light bulb. Instead, we do have transfers of energy. So I can draw those. First of all, I have some electrical work coming in. So let me just let me write it like this, and then I'll explain it. This is, the W represents work. The dot on top of it represents the time rate of change of work. So time rate of change of work is just power. And then I put a subscript ELEC here to indicate that it's electricity. So this is the electrical power. And I've drawn an arrow across the boundary to indicate that it's coming into the light bulb, because we have to put electricity into the light bulb to make it work, right? So this is an example of a work transfer across the boundary, okay? Now, another form of energy transfer across the boundary would be the radiation coming from the bulb into the surroundings. So I'll indicate it like that. So what this represents is, when the light bulb is turned on, it generates some light, some heat, right? And that goes off into the surroundings. And those are forms of essentially radiation or heat transfer out into the surroundings. And so I've drawn, I indicate that heat transfer with a Q dot. So Q is frequently used in thermodynamics for heat transfer, so energy transfer via heat. And then again, the dot means that it's the rate at which heat transfer is occurring. And I've drawn the line going across the boundary and outward to indicate that it's leaving my system. Now, you don't have to necessarily get the arrows correct in the correct direction. Just like with the free body diagram, you draw a force acting in a particular direction, and then when you work through the analysis, and if you find that the force is negative, it means you had the direction wrong to begin with. Same sort of thing with these EFDs. If somehow I'm analyzing for the heat transfer coming out, and I get a negative sign for Q dot, that means that the heat transfer was in fact going in. So the signs will work themselves out. Often, though, you can reason out just pretty easily which direction the work and the heat transfer are going in. So this right here is an example of an energy flow diagram for a light bulb. Right? We've identified our system or control volume with the dashed line. We've drawn the relevant forms of mass and energy transfer. In this case, there is no mass transfer, but there is energy transfer via power. And I've, again, indicated it with an arrow showing where it's occurring, indicating that that's a work, time rate of change of work kind of interaction. And then I've drawn here the heat transfer coming out, indicated that with an arrow with a Q dot here to indicate that that's a heat transfer. So I've shown the relevant transfers of mass and energy. And as I mentioned before, I have some other examples online. I won't go through them here, where you can see I do this sort of thing, for example, with a hair dryer, with a pump, in a motor, things like that. So you can see some more examples. We'll be doing these sort of energy flow diagrams frequently throughout the course. They're very fundamental. You need to do it to all of your systems or control volumes that you analyze using, again, conservation of mass, the first law of thermo, and the second law of thermo. So you'll be doing this all throughout the course. Let's see, what else I want to mention here about working problems. A few other things. Well, you know what? Let me go on to the next set of material here. And I'm going to show this, my view of engineering modeling. I say another view of engineering modeling because the standard approach to solving problems in this particular course, ME 200 at Purdue, we have a particular format for solving homework problems that was developed long ago, and it's kind of a rigid structure that the instructors like you to follow. But I want to just kind of give you a different view on how we do engineering modeling. So I'm going to go through these various steps I have on the screen. So the way I view engineering modeling based on my experience is that, first of all, what we develop engineering models to make decisions. Okay? So what we do is we see something in the real world and we want to make a decision about that, and an informed decision. So often those decisions can be based on experience, prior experience solving a similar problem, etc. But in many cases, we like to have some sort of a model or some sort of analysis that can support our decisions, help us make the right decision. Okay? So first thing we typically have to do is clearly define the problem that we're going to model. Right? So we see something in the real world, we need to make sure that our model is reflecting that reality to a sufficiently good degree so that we have confidence in our predictions. So one of the things we want to do when we define that problem is, what is it that we want to know? What do we want to predict? Models aren't going to be able to predict everything. One model can't do it all. So, in thermodynamics, our models typically will predict things related to thermodynamic properties like pressure and temperature and specific volume. They won't give us predictions on like the acceleration of an object. That would be a different model that involves dynamics. Okay, so you have to identify what it is you want to know so you can develop the right kind of model. And then secondly, you want to identify the system or control volume that you'll be using. What is the system you're analyzing, or what is the control volume you're analyzing? You need to identify that, and that's where the engineering flow diagram comes into play. The second step is to actually model the problem. And when we do that, we have to identify what important physics are important in that particular problem. So, what governing equations are relevant? Is mass, conservation of mass, is that an important part of the physics in this problem? Is Newton's second law really something that's important for this problem? Is it the first law of thermodynamics, second law of thermodynamics? What fundamental relations are significant in that problem that are really relevant to our model? For example, if we were interested in looking at how much energy we need to boil water, a certain amount of water, we don't need Newton's second law for that. That physics is not important for that particular problem. The first law of thermodynamics would be important for that problem. Okay, so that's what I mean by identifying the important physics. Part B here is identify the significant mass, energy, and force interactions with the surroundings. So this is where your energy flow diagram comes into play again, as well as potentially a free body diagram if those physics are important. Then once we've identified our system, the relevant force and energy interactions, what governing equations are important, then what we do is we need to make assumptions to simplify those governing equations, right? So if we have the first law of thermodynamics, we need to apply that first law of thermodynamics to our particular system. And that's where some assumptions come into play. And so that's what I've written here. So, for example, are we dealing with a steady state where things don't change with time, so we can get rid of time derivatives? Can we simplify our governing equations with that assumption? Is the process we're dealing with adiabatic, meaning there's no heat transfer? That will simplify our governing equations. Do we have an ideal gas that we're working with? Is the system reasonably modeled as being frictionless? Those are the assumptions we can use to simplify our governing equations. And then we also have to identify the boundary conditions or initial conditions. That's, as you know, from solving differential equations, for example, you need to have some boundary conditions or some initial conditions in order to get kind of a starting point for the equations. So boundary conditions and initial conditions are also very important to identify. So now we've actually developed the model, right? So we've seen the real world thing. We've identified the important physics. We have identified our system and interactions with the surroundings. We've identified what fundamental relations are important, and then we've simplified them, making significant assumptions. Then it goes into the realm of mathematics. So we take those governing equations and we analyze them mathematically. So we'll simplify and solve those governing equations subject to the assumptions and boundary and initial conditions we've specified. And we analyze them mathematically so that we can make predictions of what it is we were interested in. Back up here in the first step, we said, what do we want to know? Our mathematical analyses are meant to give us predictions for that. Okay, so we might predict, how much energy has been transferred, what acceleration do we expect to get, how much time does it take to complete some process. Those are the predictions we're looking for. Once we have those predictions, one of the first things you want to do is ask yourself, are they reasonable? If you get, if you're predicting, for example, the pressure in some container and you get a pressure of 10 billion kilopascals, that's probably unreasonable, right? You may have made a mistake somewhere. So you want to just make sure that the predictions you're making are reasonable based on your prior experience, okay? So that's one thing you want to, if they're not reasonable, then there might be a mistake in the analysis or a mistake in the setup of the problem or the assumptions. And then if you are feeling like, well, those predictions are reasonable, then what do the predictions mean in terms of the real world? We want to take it out of mathematics and back into the real world again. So, if you get a prediction of pressure in a tank, you might ask yourself, well, okay, I think that pressure is reasonable, and you want to interpret that pressure so you can make a decision about the real world. Actually, it kind of bleeds into this point number 5. Make decisions based on the predictions. If you make that pressure prediction, then you can start making decisions. well, that given this pressure, I need to make my tank the walls of my tank a little bit thicker. Maybe I can get away with a little bit thinner. Need to beef up the structure over here, that sort of thing. So this part B and 5 actually kind of blend into one another. Also, if the predictions aren't accurate enough to make confident decisions, then you need to improve the model and start over. So this is something important that a lot of people don't really realize, is that you don't have to have super accurate models all the time. Many times in engineering, you just need to make like a yes/no type of decision. You know, do I expect a quantity to increase or decrease with time? I don't need to necessarily know by how much. I just need to know whether it's going to go up or it's going to go down, right? So you don't need to have a super accurate model that's accurate to within 12 decimal points or something like that. It's just not necessary. The precision in your modeling depends really on how much precision you need to make your decision, okay? So many times models can just be useful in a qualitative sense. You know, like I said, something increasing or decreasing. Is something going to be positive or negative? Or, you know, getting orders of magnitude. Is something going to be, you know, have a range of values in the hundreds or range of values in the 0.1s, right? So, but if you find that your prediction's too coarse, you know, it's not good enough, then you might have to go back and add an additional complexity to your model to make it better, right? So you need to evaluate whether or not your predictions are accurate enough to make good decisions. If you find that your model is good enough to make the decision, then that's good. You're done. You know, you've done what you need to do. Okay, so my general approach has always been to start with the simpler models with the basic physics in it, and then see if that's good enough. And if that's not good enough, then I go back and refine the model. What I don't do is try to throw every complexity in the first step, and then because then it gets really complicated and it's easy to get bogged down and hard to debug when mistakes are made. So my philosophy is to start simple and add in complexity as you need it. The last item here is one that I'm going to talk about in more detail after this page, and that is clearly communicate your engineering analysis. You know, these kinds of models aren't developed in a vacuum. You need to usually interact with your colleagues on them. You need to describe them to your colleagues, perhaps your supervisors. You have to support the decisions based on your model, so you're going to have to describe your model. So that involves describing in text, figures, mathematics, and plots. All of these previous steps, you need to be able to support those, the model steps that you've taken. So you have to document them. And they have to be done in sufficient detail so that others can follow your analysis. You know, it's best to write all these things down, because even though you know what you're doing, other people don't necessarily know what you're doing. So you have to be able to communicate that to them. And keep in mind that in most cases, people will rely on written documentation of your work and not a verbal description. So it's essential that you develop good written communication skills. That's very true. You know, you'll be making a lot of presentations and interacting with people, you know, face to face during your careers, but the written documentation you prepare, that goes out much more broadly than like the number of people in your in a conference room, right? Written documents are archived, they're shared, you know, company-wide. People might look at them 10, 20 years later. So that having good written communication skills is very important, okay? In fact, that's what I'm going to continue to talk about in the rest of this video, because it's so important. So I have a document attached to the notes here, advice for preparing written assignments. I'm not going to read through this giant wall of text here. It really wasn't meant for me to read through it, but you can look at it on your own. But I just want to emphasize how important developing good written communication skills is. One of the things that we do, and most engineering departments do this, is we go through a periodic review of our program, and we ask our stakeholders, which include employers who hire our graduates, you know, and we ask our graduates at some point later in their careers, you know, what skills did you find important while you were while you're in your job. What kind of skills are important when you hire someone? What kind of skills do you use in your job? What are the most important things? Is it technical skills? Is it ethics? Is it design skills? Is it communication skills, etc.? And what we have gotten back every time we do this process is communication skills is usually at the top of the list, often higher than technical skills. So having good communication skills is absolutely important. And the only real way to get good at communicating ideas is practice. So I encourage you, while you're at a university, to practice those communication skills, practice good communication skills. And so you can make mistakes in this university environment and get feedback, and the stakes are low. If you do poorly on some writing assignment and you get a C, for example, that's fine. You can live through that. That's not a big deal. But if you do a poor job of writing a proposal that is, for $1 million and your company's depending on it, you may not be able to recover from that, right? Your job is on the line in that situation. And so you want to develop the skills here where the stakes are low and you can get feedback rather than when it's really important, okay? So I've written some thoughts I have on this in this document, and like I said, I'm not going to go through the whole thing, but in this course, where you develop those communication skills or where you apply them is really in solving homework problems, quiz problems, exam problems, and in any communication via email and such that you do with the TAs and the instructors. So as far as email and with instructors and TAs, just always try to write professionally, use proper grammar, just kind of practice those things. Usually emails are short, so it's not like a big effort. When you write your email, just kind of proofread it before you send it off. So get a little practice there. As far as quiz and exams, there's a lot of flexibility. Those are timed events. You're under a lot of pressure. We don't really expect perfect communication skills in those environments. But when you do homework, you have a lot more time. We do expect you to do a good job communicating your solution analyses when you do the homework. And so probably the thing that I recommend the most, again, you can read what I have on the page here, but what I recommend the most is to emulate the solution methodology. So I have here, if you look through the written examples that I post online, that's the solution methodology I highly recommend you follow. Okay, so I'm showing on the screen one example of that. So here's a typical homework problem. So here's the problem statement, and then the solution. So if you take a look, I'm not going to go through all the technical steps here, but I've identified some parts that I think are kind of important. One thing, for example, is identify the system and control volume. So this is a piston cylinder kind of problem, and you can see I've identified the system of interest. I showed an energy flow diagram, so in this case, we've got some heat transfer coming in here and some work being done on the surroundings, namely the water doing some work on this piston. So I described this before, identify the system, draw energy flow diagram. I think it's worthwhile to guide the reader with some explanatory text. Don't just start with a bunch of equations, right? I actually kind of describe what it is I'm going to do in words first before I do it. When I write equations, I write the equation in symbolic form. I don't just start plugging in numbers at the beginning. It would be super hard to follow if you just start throwing around numbers. So put the equation in symbolic form. I often put equation numbers so it's easy to reference it later. I can come back later and say, substituting equation 1 into equation 3, we get the following, right? It just makes it easier to follow. Now that I have my equation, I can then identify all the variables and including units and how they were found. So you can see here in this equation I have an x1 and a vf1. So I just list them. X1 is 0.25. That was a given in the problem statement. Vf1 is this value, and that comes from a particular table. I'm just making it easy to follow. Going further down, you can see here when I actually solved for one of the things that was asked for, this x2 quantity, I put a box around it so it's easy to find. And in engineering, typically, our our solution, our values, our numerical values that we solve for, go out to 3 significant digits. You can see 1, 2, 3 here. Don't write answers out to 6 significant digits or whatever your calculator can go to. That's too much. You don't know these values that accurately. If you do that in the real world, and I've seen people do that, then immediately people question your judgment. If you don't have enough engineering knowledge to know that presenting a result out to 6 significant digits is inappropriate, then they kind of question everything else you've done. 3 significant digits is sufficient. Now, I know that there's a whole procedure for analyzing how many significant digits should be used, depending on how many significant digits are given, etc. You don't need to go through all that. Just keep in mind, in this course, 3 significant digits is what you really want to go to. There'll be some exceptions to that, as we'll talk about later in the course, but 95% of the time, 3 significant digits for your final answer is appropriate. It's okay to put more significant digits throughout your calculations. You can see up here, for example, the VF1, this value comes from a table and it has many significant digits. What is it? 5 significant digits here, right? 1, 2, 3, 4, 5. It's fine to keep carrying along more significant digits earlier in the calculations, but for your final answer, keep it to 3. Okay, so anyway, the main thing in the communication part is I've boxed it in and I used a reasonable number of significant digits. And then kind of going on further, here I had to actually do some derivation, like there's an integral and I show kind of the steps of the integral. So just kind of show the derivation steps. Don't do too many steps in your head. It's easy to make mistakes that way. But and again, importantly, if you do a lot of steps in your head, then it makes it harder for someone else to figure out what you did. You're not communicating your approach clearly. Okay. And then once I get my final result here, I did a little bit of a kind of an interpretation of the result. I got a positive value for work here, so that means in this analysis that work is being done by the system on the surroundings. So a little bit of interpretation of the results is worthwhile. Here's an example where I use the first law of thermodynamics, and then I mentioned below it I'm neglecting changes in kinetic and potential energies. So that's, I'm stating assumptions where I use them. So I think that's important. You just write down your governing equation, as I mentioned before, and then you make simplifying assumptions. And you need to write down what those simplifying assumptions are. And then the last thing I'll show in this solution methodology is like I had to put in a plot. So you can see the plot here, and I've labeled my axes down here. Normally, actually, let me fix that. This should say pressure. I did actually have this in the document I prepared, but for some reason it didn't show up here. It's a specific volume. It's usually a good idea to put in words what the variables mean. So pressure P, specific volume V. Only if everybody knows very confidently what P and V stand for should you just use P and V. But it's usually a good idea to put the word and then the symbol. So you label your axes so everyone knows what the axes are. I've identified some states and some values. I've just done a good job of documenting this figure. That's really what I'm trying to point out here is I've put all the necessary information in the figure as well as kind of a little bit of description of what's happening here. The bottom line is with these solutions is, I want you to try to emulate the style that I use. And the reason, hopefully you find that the solutions I prepare are good at communicating all the different steps. Imagine if I had just started with some numbers right away in an equation that you don't know what the equation is, you don't know what assumptions I made, and I just chugged through a bunch of numbers out to 6 significant digits and then just got a final number. I think you would find it confusing. You wouldn't really understand what I was doing, and you would get frustrated and find it difficult, right? So you don't want to do that. That's not the approach you want to take, right? In your work, start practicing communicating all the steps clearly so that others who are using your work won't get frustrated. Okay, so anyway, read through this document. I'll make it available on the course webpage in more detail, or you can, as I kind of scroll through this slowly, you can pause the video and just read it on the screen. So I'll just kind of slowly scroll through it. There's a lot here, but it's a lot of this is just sort of small stuff. Okay, so there, you should be able to pause the video wherever you need to there. So I think that's all I really wanted to say. Let me just quickly scroll to the bottom. Yeah, that's all I really want to say for this particular lecture. Let me just kind of recap. Engineering flow diagrams are important, so I went through that briefly. Take a look at the examples to see how we prepare those engineering flow diagrams for a couple of other situations. They'll be used all throughout the course. When solving problems, work on your communication skills. Try to do a good job of making nice, neat, very explanatory kinds of solutions. Follow some of the guidelines I've written down. Try to emulate the approach I take. And that typically involves identifying your system or control volume, doing an energy flow diagram, writing down what governing equations are important, what physics are important. Start with the basic equation. Don't simplify it at the first step. Just write the full basic equation. Then make some significant assumptions that you use to simplify the governing equations. Do your mathematical analyses in sufficient detail so that people can follow the work and you can easily debug it if there's a mistake. Tend to do things symbolically as much as you can. And then if you start plugging in numbers at the end, identify where those numbers come from. Just kind of make it clear, A is equal to this, B is equal to this, and they come from the following table. When you have a final answer, box it in so everyone can kind of see it. Use only 3 significant digits for the final answer. Interpret the final answer if needed. And then make sure any sort of plots you make are all clearly identified and such, easy to follow. Okay, we'll go ahead and end the lecture there.